In the last class, we talked about heuristic techniques and heuristic function, and we have the classification of heuristic function. There we have admissible and non-admissible, and we have um, also explained um, what admissible and non-admissible is with an example. And then um, today we are going to look at heuristic. Uh, okay, yeah, today we're going to look at hill climbing technique. Okay, so this is what we are going to do today. Hill climbing. If you have not heard of this term before, um, well, hill climbing algorithm, okay, it's a local search algorithm and that continuously moves in a direction of increasing elevation to find the maximum value of the mountain or a hill. Okay, or in other words, you can say that tries to find the best solution to the given problem. Okay, so as you can see here, objective is to find the best solution. Okay, and here in this hill climbing, your best solution would be to find the peak of the hill or the mountain. And how is this searching done? Searching is done by continuously moving in the direction of increasing elevation. You are going to move in this direction. Okay, and this process um, terminates. When you have to stop when it reaches the highest value. When there are no neighbors which have higher value than the current value. That's when you have to stop. And one example that make use of hill climbing technique is traveling salesman problem. And this kind of technique, hill climbing technique, it is also called greedy local search. Why? Because it only looks to its good, it only looks to its immediate neighbor state and not beyond that. Okay. And um, in this in hill climbing algorithm, the node has two components. One is the state and another is the value. Okay. And one more thing about this is that in this algorithm, it is not required to maintain the search tree. Okay. The search tree or the graph, as it keeps only a single current state. Fine. Now, let's move on to the next. What are the features of hill climbing technique? Okay, so there are three features which I have written down here. First is generate and test variant. The second is greedy approach. And the third is that it requires no backtracking. Now let us look at the first feature. What is that? That is generate and test variant. Okay, so hill climbing technique, okay, is the variant of generate and test method. And this generate and test variant, okay, it comes under informed search technique. Okay, just hold on. All right, so this comes under informed search technique. All right. Mm. Let's get back to this. Yeah. So this comes under informed search technique. And it uses depth first search with backtracking. And there are two modules which are generate and test. Right? Just hold on 1 second, please. Let me share my screen once again. All right. So, what are these two modules doing? The generate module generates all the possible solutions, and the test is um, testing all the possible solutions that are generated. Okay. And what you're going to do is, if the solution, okay, if among these possible solutions, when you test it, if that solution passed the test, then the solution is accepted, else you drop that. Okay. And how do you know that the solution has passed the test? That is, if that if that particular solution that you're testing matches the goal state, the goal, okay, then that means that it has passed the test. And this method, it produces feedback, okay, that helps to decide which direction to move in the search space. Fine. Next point, greedy approach. um, Hill climbing algorithms, search moves in the direction which optimizes the cost. Okay, no backtracking. In this hill climbing technique, you don't have to backtrack the search space. And you don't backtrack, I mean, you don't backtrack the search space. Okay, um, and because it does not have a memory to remember the previous space. Okay, just all right. Now let's go and head on to the next. As you can see on the screens, state space diagram for hill climbing. What is this state space diagram? It's a diagram for hill. Um, it's a diagram which is graphically representing the hill climbing algorithm. Okay. Basically, it's showing a graph between various states of algorithm and the objective function or the cost. Okay. For example, as you can see here, I'm drawing this. In your x-axis, suppose we're taking the states, we are taking x-axis as the state space, and y-axis we have the objective function. Okay. As I have written here, if the function on y-axis, okay, if the function on this y-axis is cost function, then the goal of the search is to find the global minimum and the local minimum. Else, if in case of objective cost, you are taking on the y-axis objective function, then your goal of searching is to find the maximum, the local, the global maximum and the local maximum. All right. Okay, so let me, we have a diagram here. I have drawn it here. Um, and this is the graphical representation, okay, of the algorithm. And these are some labels which are have labeled for all this. Let me define them, okay, one by one. Okay, so local, first let's go to local maximum. What is local maximum? Well, local maximum, it's a state. um, okay, where do we have local maximum here? Okay, local maximum is here, right? It's a state which is better than the other neighboring state, but that doesn't mean that that is the highest peak or that is the best solution. There is also another state which is higher than the local maximum. Okay. And what is that higher state called as? That higher state is the global maximum. What is global maximum? Global maximum is the best possible state of the state space landscape. And as I have just said, it has the highest value of objective function. Okay, current state. Here we are taking, we're just assuming this as the current state, right? So what is current state? It is a state in a landscape diagram where the agent is currently present. Okay, where the agent is, where the agent is currently, that is the current state. And we have another label that is flat local maximum, this area, okay, this area. What is this? This is a flat space in the landscape where all the neighboring states of the current state have the same value, right? Soldier. Soldier is a plateau region which has an uphill edge, okay? Now, um, we have different types of hill climbing technique. As I can see it on the screen. Um, One of our hill climbing technique is simple hill climbing, and the second type is steepest hill ascent hill climbing. Okay, and the third type is stochastic hill climbing. Today we will do a little bit about simple hill climbing and steepest ascent hill climbing. Okay, so let me just say, give an overview of what a simple hill climbing is. As I have just said that um, this hill climbing is a technique or an algorithm that is used to find the best solution, right? The peak of the solution. And how it does is it moves in towards a increasing elevation, right? So this is what we're going to do now. Just wait a minute. Meanwhile, you can read through the screen the points that I have written there. All right. So simple hill climbing is the simplest way to implement hill climbing algorithm, right? And um, it only evaluates the neighboring state at a time and selects the first one, which optimizes the current cost, and it sets as the current state. In other words, you can say that it only checks one successor state, okay, or one neighboring state at a time, and then it finds if the neighboring state is better than the current state, then it moves forward and it makes that new state, okay, as the current state. Else, if it doesn't find any better neighboring state, then it remains in the same state, okay. And because yeah, okay, so because it uh, considers only one neighboring state at a time, okay, it is less optimal, okay, and the solution is also not guaranteed. It is also less time consuming, okay. So for example, if I have to explain this hill climbing technique, so we have suppose this a hill, okay, this is our hill, and our objective is to find out the highest point, or this peak of the hill, okay, somewhere over here. We have to find out that point, what that point is. And when I say point, okay, um it's the same as operator here in this case, okay. Operator and points, they mean the same. Okay, so we are going to take different points in this hill, and we're going to continuously keep comparing two consecutive points. For example, I'm here, this is my origin, and I'm going to compare it with the um, next point or the neighboring point. These are two consecutive points. I'm going to compare these two, and if one is better, if the neighboring state is better, then I'm going to make this my current state, and then again I'll compare it with the next neighboring state, okay, and so on. I'll continue and do this, right? And if when I compare these two or whatever these two, okay, and if I don't find that the neighboring state is better than the previous one, then then I'll remain in the same state, okay. So uh, you're going to keep on continuing to do this, and you're going to terminate when you have just said now. When are you going to terminate that? Just the terminating condition when it reaches the highest value. When do you know that it has reaches the highest value? When there are no neighbors with higher value than it, right? That's what I'm saying, right? If yeah, if you don't find any other point which is higher than the uh, new value, right, then that is the peak. Okay, that is the peak. All right, so I think that's all. And tomorrow, in the next class, um, algorithms of this simple hill climbing will be given in detail in a stepwise manner. And next, let's have an overview of what steepest ascent hill climbing is. Steepest ascent hill climbing is it's a this is a variation. Okay, it's a variation of this the previous algorithm, that is hill climbing algorithm, simple hill climbing algorithm. And what's the difference between these two is that unlike simple hill climbing algorithm, this algorithm, it is examining all the neighboring nodes, right, of the current state, and and it selects only one neighbor node which is closest to the goal state. Okay, um in the previous one it examines only one neighboring node at a time, right? Here it examines all the neighboring nodes of the current state, and among the all of the neighboring state, which kind of node it is selected is the node which is closest to the goal state, right? And this algorithm consumes more time because it searches multiple neighbors, right? So yeah, that's a little bit about steepest ascent algorithm. Next class we will do in detail about all these three algorithms. Mm, yeah, that's all. Thank you.